multiplication.
Okay, thank you. So it's another talk on matrix multiplication, and so we are studying the same things. I will first give an overview of the results before going through details. So we are studying the same thing as in other talks, so the exponent of matrix multiplication, and we want to, more precisely, to study upper bounds on this omega, the exponent of matrix multiplication. So this is another table describing the main improvements on the exponent of square matrix multiplication. And today's talk will be about this slight improvement over the result by Vasilevska-Williams. And so all this improvement, so after Strassen upper bound 2.48, were obtained by using a method called the laser method. And more precisely, the laser method was introduced by Strassen. So it's what I call the version 1 of the analyze by the laser method. And then all the other papers, so the other successive improvement were obtained by considering more and more complicated tensors. So in particular, the size of the tensor increased, and in order to analyze it, more generalization of this analyze based on the laser method was needed. So this was the laser method, I will call it laser method V2 for what's done by Koper-Smith and Winograd, and then V2.1, 2.2, 2.3. And well, the point is that all the previous versions, so up to version 2.2, require to solve a complicated optimization problem, which was very difficult when the size of the tensor increased. And with this version 2.3, we can analyze the tensor in time of polynomial in the size of the tensor, because the analysis is done through convex optimization. Okay, so it's the main difference between this version and the other versions. And so our method can be described. So we can take, if you take any tensor for which you can obtain an upper bound on omega using the laser method, using our technique, so based on convex optimization, we can obtain the bound in polynomial time. And the question is on which tensor we want to apply this. Well, we don't have many candidates. So what we will do, we will apply this analysis on the powers of the basic tensor from the paper by Koper-Smith and Winograd. And so this bound, 2.376, was obtained by considering the second power of this tensor by Koper-Smith Winograd. The improvement by Stosser was obtained by considering the power 4, so the number of variables in the optimization problem increased, 9 here. And then Virginia's result was obtained by considering power 8, so 29 variables. And what we obtain is this very slight improvement by considering power 16 and 32. And the number of variables is quite high, so we really need our approach based on convex optimization to be able to obtain the numerical bounds corresponding to the analysis. Okay, so now I will go through more details. I will first start by explaining how to obtain upper bounds. Sorry, it's not lower bound, upper bounds. I don't know. Upper bounds on omega. So it has been done in the previous talk, so I will be will do it very quickly. So we have Strassen algorithms which show how to compute the product of two 2x2 matrices using only 7 multiplications. The point is that you can apply it recursively, and for product of matrices of size 2 to the k, you can do it with 7 to the k multiplication, so this gives you this bound. So this gives you one technique which was called the technique number 1, the approach number 1 in the previous talk. It seems that if you are able to show that you can compute the product of two m by m matrices using t multiplication, then you obtain a bound on omega immediately using this formula. And so Strassen algorithm is the case m equals 2 and t equals 7. And we will see how it's related to the rank in a few seconds. Okay, so we will focus on, we'll study the tensor of matrix multiplication, the same definition as in previous talks, with the same notation, so bracket m and p. So this is a formal sum, but you can interpret it as a tensor, so an element in the tensor product of three vector spaces. Well, generally a tensor over an element of these vector spaces can be written as a formal sum of this form if you consider a basis of the three vector spaces. And the definition I gave of the tensor of matrix multiplication for the case where the dimension of U is Mn, dimension of V is Np, and dimension of W is Np through this basis and these coefficients. Okay, so it's the same tensor as in previous talks. Okay, so now the rank, where I will use R to denote the rank. So the rank of this tensor is, of course, upper bounded by M, N, and P. And the Strassen algorithm shows that the rank of the tensor of matrix multiplication of size 2, so 2 by 2 matrices, is at most 7. The point is that the rank represents the number of multiplication of the best algorithm for the matrix product. And so we can rewrite what I explained a few minutes ago by this inequality. So if you can show that the rank of this matrix, the tensor of this matrix product is smaller than t, then you obtain this inequality, which gives you a bound on upper bound on omega. And you can generalize it to rectangular matrices, and you can also generalize it. You can replace the rank by the border rank, and since the border rank can be smaller than the rank, this gives you a better bound in omega. Okay, and the third generalization is the third approach in the previous talk. It's the asymptotic sum inequality. So if you can show that an upper bound on the rank of a direct sum of two matrix products, then you obtain an inequality involving omega, and so this gives you another way to obtain an upper bound on omega, and you can generalize it with a direct sum of more than two terms. This is called the asymptotic sum inequality, and we will use it a lot in this talk. Okay, so the first two bounds here were obtained by analysis of the rank, so the first technique. This one by analysis of the border rank, and this bound by the asymptotic sum inequalities. And the last 5 bounds obtained by techniques that I will now explain, which is the laser method. Okay, so I will first work out the laser method on a simpler example. It's not very simple, but it is simpler than the full tensor by Copper-Smith and Winograd. So first, why it's called laser method? Well, I don't really know the answer, but Strassen wrote a paper and where he gave one possible explanation of this term. Said that it is reminiscent of the generation of coherent light. Okay, this is the only at least published explanation I have of the name of a laser method. And so this reference was this bound, so the 86 paper by Strassen, and all the further improvement also use variants or successive improvements of this method. So I will now describe the method and then the improvements. Okay, so I will start with what I said, the simpler example, which is the first construction from the paper by Copper-Smith and Winograd, which is a sum of 3 terms. It was the same. It was also presented in the previous talk. Okay, so in this case, we have all the vector space are dimension q plus 1. So we have q plus 1 x variable, q plus 1 y variable, and q plus 1 z variable. And so it's the sum of these 3 terms. Okay, so this is a tensor isomorphic to this matrix product. Why? Because, well, you can you can add a dummy index 0, 0, 0, and you see that it represents the multiplication of a 1, 1, 1 by 1 matrix by a 1 by q matrix. And you can do the same for the other two. The second is isomorphic to this, and the third isomorphic to this. So these two parts, these three terms represent matrix products. Okay, and the point is that it's not a direct sum because some variables are shared. Okay, here you have the same zi variables here, and the same xi variable here and here. Okay, so variables are shared, so the sum of the three terms is not direct. Okay, and well, you can give a more algebraic description of this decomposition into three terms. So you can consider this decomposition of U, this decomposition in V and W. So U decomposed on U0, U1, where U1 corresponds to variable x1, and U0 to variable x1, and U1 to the other variables. And you can see that this part is a tensor over U0, V1, and W1. So that's why we use the superscript 0, 1, 1. And the same here and the same here. But the same interpretation with this time this blah blah 1, 0, 1 and 1, 1, 0. Okay, and this is not a direct sum because the variable lies in the same space here and here, for example. So it's not a direct sum, so we cannot use the asymptotic sum inequality. Okay, but the trick to the essence of the laser method is to consider higher power of this tensor. So for example, consider the power 2. So the power 2 is the sum of 9 terms. Okay? So more generally, you can consider power n. It will be the sum of 3 to the n terms. And so I should mention, well, I can mention it's really related to the talk by Chris. Here we will use the fact that the rank of this is upper bounded by n times by q plus 2 to the n. But if we are able to improve this upper bound by q to q plus 1 to the n plus something, that it will imply omega is equal to 2. Okay? So this is to put a relation, to show a relation between what I'm explaining here and the conjecture in Chris' talk. Okay, and so we have 3 to the n terms. And Coppersmith and Winograd showed how to select among the 3 to the n terms this number of terms that do not share variable. Okay? And if they do not share variable, this will be a direct sum, and we will be able to obtain an upper bound on omega using the asymptotic sum inequality. Okay? And by select, I should be more precise. The point is that you can select it by only zeroing variables. So this kind of selection will not modify the ring, will not increase the ring. This is a crucial thing. So this will be a restriction of the initial tensor. And the precise statement of this result by Coppersmith and Winograd is the following. So this tensor, so the nth power of TEZ, can be converted, so again by zeroing variables, into a direct sum of this number of terms, and each term containing this number of copies of the first part, and this number of copies of the second part, and n over 3 copies of the last part. Okay, here H represents the entropy. So if you do computation, this entropy is equal to this, so you can rewrite this term as follows. And so n copies of each part has the following meaning. So when you take the nth power of TEZ, you will obtain 3 to the n terms. And yeah.
Could you give some intuition why this entropy shows up?
Yes, I will give it in a few minutes.
Okay.
Yes, if it is okay. Yeah. Yes. So we have you have this number of terms, and the first term represents n copy of the first part, the last one n copy of the last part, and what the theorem is saying is that you can select many terms, and this term will not be of this type, not of this type, but between them, balanced. The same number of copies of the first, the second, and the third. Okay? And a term isomorphic, so containing this number of copies, is isomorphic to this. So we know that it is isomorphic to this matrix product from the fact that each part here is isomorphic to a matrix product. And then you can use the asymptotic sum inequality, and so this gives you, so this, we compute this gives you this. So because we have here this term here, and we know that mi, ni, pi are all equal to q to the n over 3, so you obtain this inequality. So now the rank of this is at most the rank of TEZ to the power n, which is q plus 2 to the n. Okay, and then you do the numerical computation, so you take power 1 over n, and you do the optimization, and you find that the best value is q is equal to 8, which gives you an upper bound of 2.403. Okay? And I will try to give an idea behind the proof. Okay? So I will, let's consider the case n equal to 2. Okay, so we have 9 terms. So let's consider this term. Okay, so what is this term? So you can compute it. It's the tensor product of the first one and the second one. So this is equal to this. So it's a tensor about over this, well, it's tensor in this vector space, an element of this tensor space. And if you look at the subscript, so you have 0, 1, 1, 0, 1, 1 here. So we will label this term by this list of subscripts in this order. Okay? So this one is labeled 0, 1, 1, 0, 1, 1, and the other 9s are also labels. Okay, so we have 9 labels. And so let's consider the first 2 here. So you can write it as the label is 0, 1, 1, 0, 1, 1, as I explained. Here the label is 0, 0, 1, 1, 1, 2. And I said we want to extract terms. We do not share variables from this sum of 9 terms. And you see that these two terms share variable. You have the same zi tensor zi prime. So we need to remove them. And the fact that they share variable can be seen directly from the label. We have the same label here, 1, 1, and 1, 1, the same green part of the label. And we can remove this term, for example, by setting all the variables in V1 tensor V1 to 0. Okay, so if you do this, this will remove this term because it has a variable in this space. Okay, but the point is that this will remove this, which is good for us, but it will also remove other terms. Okay, so there are a lot of collateral damage in this technique. We want to remove one term to avoid to make the sum direct, but if we try to do it, this will remove many other terms. So you have to do it very carefully. Okay, so now we have this one. So now we can analyze, let's say this one. So there is no conflict between the labels here, so you can keep it. But then there will be a conflict with the other one, so you will need to erase, to remove this one, and you can do it again by zeroing variable if you do it. For example, by zeroing variable in these spaces. Okay, so the conclusion is that you can convert the second power, consisting initially of 9 terms, into a direct sum of 2 terms. And you can do it only by only zeroing variables. So the next step is to consider power n. So in power n, as I said, there are 3 to the n terms. And in this case, each label will consist of binary strings of length 3n, so 3 parts, and length 3n. And this theorem states that we can obtain from this sum of 3 to the n terms this number of terms, so this number of labels that do not share a blue part, a red part, or a green part. And moreover, the theorem states that the label will all have this form. So the blue part will consist of n over 3 zeros, 2n over 3 1, and the same for the red label and the green label. And this is a very strong construction, very powerful construction. So it is here that the entropy appears. It's that if you look at the number of possible strings, blue strings, here under this condition, this number is given by this combinatorial coefficient. And this combinatorial coefficient is essentially this thing, the entropy, the exponential of the entropy. Okay. And the theorem states that actually, yes, you can saturate this bound up to minus 0.1 here, negligible term. So you can do the best. You can really almost saturate this bound. It's a very strong theorem, and it's based on a quite complicated construction using the existence of dense sets of integer with no 3 terms arithmetic progressions. It's a quite complicated and probabilistic argument on the existence of such a way of converting the sum into direct sum of this number of terms. Okay. Does this answer your question about the entropy? With at least some feeling about it.
Well, so, yes, I mean, I think of entropy as like this channel capacity.
Yes.
And
yes, so there is no deep reason why it is the entropy. Virginia yesterday explained everything using the combinatorial coefficients. And the point is that combinatorial coefficients can be expressed using the entropy.
That's the main reason.
yeah, I mean,
So it's the only thing, there is no deep,
then I need to think about why that.
And I use entropy.
Shannon's paper.
Yeah.
It's just using
But if it was simple entropy, you didn't have any of this, hard results like that. Simpler entropy means that you have certain, let's say, letters of, let's say, of length 6 and what are combined. But here you claim that this is much more difficult, right? This is based on some non-serial arithmetic progression. So that's
Yeah, the little o of 1 is.
No, it's because we like have 3 sources.
So it's a.
Yeah, but that's
So I simply use this equivalence.
But so why do you need this?
Yeah, the point is that the entropy is concave. And this is the reason why we will be able to do the conversion, to do the optimization problem using convex optimization.
But the binomial coefficients are also larger than the convex. So,
Yes.
so you're just using that as well. Or
Yes, we will use the fact that everything will be convex. Yes.
But binomial coefficients are known to be larger.
Yeah, of course. Yeah. So, of course. Yeah. You do. It's not. I mean, it gives you a simple way of seeing that it is convex or concave.
Okay.
Yes, but of course you can do the same analysis without using the entropy.
I think it was done.
Yes, it depends what you prefer. So, and now I will give the general formulation of the laser method, and actually a reinterpretation in terms of entropy and some kind of penalty terms. So to do this, we'll need the notion of value, the value of a tensor. It's exactly what Virginia explained yesterday morning. So the definition of value is motivated by the asymptotic sum inequality. So in order to use and obtain good bound for the asymptotic, using the asymptotic sum inequality, we need to convert a tensor into a direct sum on many matrix products. And the way of expressing the contribution of a tensor to this left term is expressed by the value. So technically, the value for any row from 2 to 3 and any n is the maximum of this quantity over all restriction of the nth power of the tensor isomorphic to this. So you're considering all ways of converting by zeroing variable or even doing more general restriction this tensor into something like that, and you take the ways that maximize this quantity. And the value is considered as the asymptotic value of this quantity. So we are taking the power 1 over n of v rho to the n. And the limit exists. And it's called the value of t. Well, actually, technically speaking, this is a definition only for symmetric tensor. If it's not symmetric, we need to symmetrize using the cyclic shift of coordinates. Okay. And some properties, so the value of m and p, the tensor product here, is m and p to the rho over 3. Okay. And this is an increasing function of rho. Okay. And it is super additive and super multiplicative. Okay, those properties were discussed by Virginia yesterday. And so, for example, if you look at the theorem by Kopernikus and Winograd, so they say that this tensor can be converted in this number of direct sum of this number of terms, which are isomorphic to this. So this simply shows that the value with the n here of TEZ is at least, so this term, multiplied by the value of this, which is this. Okay, and if you take a power 1 over n, you obtain this lower bound on the value. And so the point is that, well, with this notion of value, you can give the following simple you can obtain the following simple generalization of the asymptotic sum inequality, that the value evaluated for rho equal omega of t is smaller than the border rank of t. It's not difficult to generalize this inequality here when you understand the notion of value. Okay, so it gives you a concise way of expressing the asymptotic sum inequality. Okay. So now I need another generalization, the decomposition of a tensor. So again, a tensor is an element in this space, in the tensor product of a 3-vector space. So if you assume that the 3-vector space U, V, and W are decomposed as direct sums of such space, then we say that the tensor T is a partition tensor with respect to this precise decomposition if it can be written in this way, so as a sum of Tijk, where each Tijk is a tensor in Ui tensor Vj tensor Wk. So it's a partition tensor if the tensor can be partitioned with respect to this decomposition. Okay? And the support will be, well, as usual, all the triple U, J, K, such that Tijk is not a zero tensor, and each non-zero Tij we will call a component of T. And we say that the tensor is tight if for any triple of this in the support you have I plus j plus k equal to d, where d is some constant. So fixed now. Okay. Yeah.
What's a tensor that's not partitioned?
Yes. So any tensor is there is a trivial.
Okay.
Yes. Yeah.
Okay.
Yes.
Okay.
Yes. So the point, yes, to fix the decomposition, you ask if you can partition it according with respect to this decomposition.
Okay.
Yes, but you're right. So any tensor has a trivial, several trivials.
So tight depends on the partition.
Yes, you fix your partition. Yes. So for example, here, well, we add our decomposition here, U0, U1, V0, V1, W0, W1. And this corresponds to the case where we have two elements in the partition here, and we have 3 components. So the support is this 3 terms, consists of these 3 terms, and it's tight because if you take the sum, it's equal to 2. Okay. So it's an example of partition tensor with respect to this partition. And now here the main theorem. of this talk, which is actually a reinterpretation of all prior works with different notations. And to make explicit that we have concave parts in this expression. So it says that for any type, so we need really that the tensor is tight, but for any tight partition tensor, so when you fix the partitions and any probability distribution over the support and any row, you have this inequality. So it gives you a lower bound on the value. Okay? And here H is the entropy. PL is a projection of P along the L's coordinate. So there's a marginal distribution. So there are three marginal distributions because there are three coordinates. And gamma P is a term to be defined later. So in the next 5 minutes, gamma P will be equal to 0. It's 0 for the simple cases. It's become a non-zero only for high power of the Cooper-Smith-Wiener operator.
So I don't see anything in your, I mean, you have rho on both sides. So
Yes. Yes, so the point.
I guess we'll see how this gets exploited. But
Yeah, you're asking how we get the lower bounds on that?
how you exploit this inequality.
Yeah, so we will exploit it by assuming that we know the values of the components. And then we know these values, so that we
So the first part is something combinatorial, like a number of different ways of selecting something.
Exactly.
And the second is, since it's going to be exponentially, it's the second term then is the cost of each component, and then there's some correction term at the end.
Exactly.
But you really want the value on the left-hand side? You don't want
Yeah.
the border rank there?
So we will use the border rank there after that to obtain the bound on.
So that's what I was wondering.
So yes, it's precisely this. So the point is that we can compute a lower bound on the value of t if we know a lower bound on the value of each component, so if we know these things. And then if we use this expression, then you can obtain an lower bound on omega. And more precisely, what we will do, we will use this implication, and we will do a binary search on rho.
What is a simple tensor? You say this gamma?
Simple, it's no mathematical definition here. It's an easy tensor. So if it is small, very small tensor, it's usually zero.
Without the gamma P, this inequality looks very familiar to me.
Yes. It's in your book. Yes. So the point is that even if the components are not matrix multiplication, and even if if each Tij is isomorphic to a matrix multiplication, you don't have any penalty term. And when it's not, then you have a penalty term. So it's the main.
You will explain that.
Yes, I will explain this. Yes. So for example, here, the support is this again. And so the probability distribution, when you can take the symmetric one, so 1/3 for each of the three terms. And actually for this, I didn't define what it is, this term, this penalty term, but for this case, it will be 0. You can compute the marginal distribution, so P1, 0, which is 1/3, P1, 1, which is the sum of these two things, so 2/3, and the same for the two other marginal distributions. And this gives you this bound. Okay? And if you remember what we had here, it's the same bound here. You see the same thing. And it's not a coincidence because there is a 1-1 correspondence between all terms. So these terms represent the number here, and the number of copies n/3 is 1/3, and this term is in correspondence to here. So this is the value of this term. So we have a 1-1 correspondence. And more generally, so the interpretation of this formula and the way it is proved is that the laser method enables us to convert by zeroing variable the nth power of t into a direct sum of this number of terms, each isomorphic to this. Okay, so this is the interpretation of this formula and the way it's proved. It's proved by generalizing the argument by Cooper-Smith. Okay, and so now we have the formula, so we can apply it on any type of tensor. So we can apply it on the Cooper-Smith-Wiener tensor, so with which was described in many talks, especially the previous one. So it's a sum of 6 terms. It's obtained by using the previous one and adding 3 terms here. And so we have your 6 terms. So this corresponds to this decomposition U, V, and W, and this time in 3 parts. And again, it's not a direct sum. So the support in this case will be as before, but with these 3 additional elements. So we know the value of each component. And what we'll do, you can take this distribution. Okay, you can take any distribution, so we can take a symmetric distribution, so value alpha for the 3 values here, and the remaining will be value 1 over 3 minus alpha for any alpha between 0 and 1/3. And you can compute the marginal distribution, and then you apply the theorem, and this gives you this bound. Okay? And if you do the optimization, you find that this gives you this bound. Okay. So after that, it's quite mechanical. And this gives you this. And so the second power, well, it's a 36 term, and you can rewrite it as a sum of 50 terms, as Virginia explained yesterday, using some merging. And then what you have 15 terms, so the support will be of this form. Then you can compute lower bounds on the value of each component. For these 3 components, it's easy because they are isomorphic to matrix multiplication. For the 4th one, it's more complicated because it's not isomorphic to matrix multiplication tensor, but you can compute the value recursively. Okay? And then, well, you choose your distribution. There we will have 4 parameters. You can try to take the symmetric distribution. It turns out to be the optimal, a good choice. An optimal distribution is symmetric in this case. So we have 4 parameters, and the sum should be 1, so actually 3 parameters. And again, you have gamma equal to 0. So if you do the numerical optimization, this gives you this above. So it's really mechanical. And so what about the 3rd power? Well, it doesn't give any improvement, but the 4th power will give it. So the 4th power this time was this number of terms, and you are regrouping. You did some merging. You will have this time only 9 parameters. Okay, so 10 family of components, so 9 parameters. But this time gamma is not equal to 0. So I should now explain what is gamma. So gamma is the max of this quantity minus this. So it's the max of the entropy over all distribution, the max of the entropy of Q, where the max is over Q, all the distribution Q, which have the same marginal distribution as P. Okay. And when the structure of the support is simple, this will be 0, but in general it's not 0, and for the 4th power it's not 0.
So just, can you give a simple example? Well, can you give an example where these things are not?
I won't give an example. There is no very simple example. I can give you an interpretation on why there is a penalty term.
That would be great.
Yes, so the point is that, so the interpretation is that the laser method enables us to convert t to the n into a direct sum of terms. It's isomorphic to something like that.
Yep.
So P, I will say that a term of this form is of type P. Okay, and what we want to do is to control P. We want to control P and choose P such that the value is optimal. But you cannot do it because you can only 0 variables. Okay? So this means that you can only control the marginal distribution P1, P2, and P3. Choosing P1 corresponds to choosing which x variable you want to 0. Okay, so you can only control the marginal distribution. So what you obtain is a non-direct sum of all type Q terms. Okay? Q satisfying this condition. And the most frequent terms are those with Q maximizing the entropy. So when keeping only those of type P, you will have a penalty term, which is large if the term of type P are not the most frequent. Okay, so that's why we have this term. So we want to optimize this.
So what's the disadvantage of taking your distribution to be the Q, the one that maximizes? Where does it cost you somewhere
So you're
else?
taking a Q, sorry, you are taking?
So just go back. So
Yes.
so you have a Q.
Yes.
Yeah. Why don't you just take Q instead of P, and then your gamma P goes to 0? Where
Yes.
do you pay? So you must have
You
to
pay
a price.
because it may not be optimal for this term, for this term.
I see. So a lower value.
Yes. 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 You're right. So we don't have any penalty. We have the same here because it's the same marginal distribution, but we may have something smaller here.
So you can take Q and then gamma will be 0, but it may give a low...
Exactly. Yeah. You can take Q, and actually, yes. So it's what is done in some several prior work. So the point is that, well, if there is no penalty term, everything is easy because it's a maximization of a concave function under linear constraints.
So is this your main contribution, this gamma P term, then? I mean,
Yes, it's really formalizing this, showing that you have a penalty term which is actually concave and...
so they use something that's non-optimal for the penalty but optimizes value more.
Yes. Yes, and then it's showing how to convert this into a convex optimization problem. I will come in 1 minute. It's just, I don't have to rush. Yeah, so if there is no penalty term, it's not difficult because this is concave, the entropy is concave. This is linear when this term is fixed. And the only condition is that P is a probability distribution, so it's linear constraints. And when it is not 0, well, it's a very nasty optimization problem. This can be done actually up to the 4th power. It's a very complicated program, but this can be done for the 1st power. It has been done by Tensors, giving this. And otherwise, it's extremely complicated. So what Virginia did is she restricted the search to the set of distribution P such that gamma P is equal to 0. But it's not a convex set. It's a very difficult structure, this set. So the optimization is still very hard, very difficult. But well, this can be done for the up to the 8th power. And after that, it's much more complicated. So what we do here, we propose a method to find a solution. This is not the optimal solution, but it will be close to the optimal solution. I mean, numerically, apparently this is very close to the optimal solution. And the way of doing this is to first find a distribution P that maximizes this expression without this term, without the penalty term. And then to find a distribution that maximizes HQ, under the constraint that Q should have the same marginal as the solution of the first problem, and then output FQ. Okay? The point is that the first problem is a concave objective function, a linear constraint, so it's easy to do. The second, the same, so concave objective function, linear constraints are also very easy to do. And since gamma Q hat is equal to 0, we know that the output will be a lower bound on the log of the value.
Sorry, what other constraints do you have in the second step?
The constraints is that the marginal distribution of Q are the same as the marginal distribution of P.
So it's just a product of the marginals.
Sorry?
It's just a product of the marginals. I mean, the one that maximizes the entropy.
It's not a product. We have Q1 equal P1 hat, and the same for the other two.
Right, but I'm saying the one that maximizes the entropy isn't just a product of the marginals.
Okay, we want to maximize the entropy of Q, of the distribution, and the condition is that the marginal distribution of Q should be equal to the marginal distribution of the distribution we have found at the previous step.
Yes, I'm saying, isn't the maximizing Q just a product of the marginals?
Maximizing Q as a product of a marginal.
The coordinates aren't independent. It's a simplex rather than a cube, basically.
I see. You have a different. Okay.
What's a linear constraint? It's important. And this gives you an upper bound, and numerically it's very close to the. It seems to be very close to the optimal solution, and we obtain this bounds by, and we can use convex optimization for that. Okay, and finally, the final slide. So what we have done, we have constructed what we call a time-efficient implementation of the laser method. So if you have any tight partition tensor for which you know lower bound on the value of each component, and for which you know an upper bound on the rank, then in polynomial time using convex optimization, you can obtain an upper bound on omega. And we used it on the powers of the basic tensor by Cooper-Smith-Wiener-Grad. And so recent result, we have shown that actually if you use the same approach and study higher powers, then this cannot give an upper bound better than 2.3725. So it's almost game over for that basic tensor. Okay. And that precise approach. Okay. So thank you.
Questions? So the same approach means merging the cells, or?
Yes. So the same approach means that we are taking only powers of 2, and we are doing exactly the same merging.
Exactly the
Yes.
same merging.
And we have another bound for any merging and any power, not a power of 2, and the lower bound is 2.3078.
And do you also have a bound for any decomposition? Not
Yes,
only
it's for. No, it's not for any decomposition. You fix the decomposition of the first power into 3 parts, and then you can have any merging and any decomposition is a merging. But yes, you only fix the first power, and you have a lower bound of 2.3 or something. Yes.
So why do you use this Cooper-Smith-Wiener-Grad tensor? I mean, what's special about it to you?
Well, do you have a better one?
Well, yes. I mean,
Yeah, no, well, yes, it's what gives the best balances on the eye. You can try to modify it a little bit, other things, but it doesn't give something better. I haven't found any better things.
is there,
But I don't have any.
Let me phrase the question in a different way. Okay, it's given good results, but is there anything that when you look at it, you say, this one should give me good results? Or is it only just based on previous experience?
I don't have an interpretation why this gives a good result. It's symmetric, which is a nice thing, but no, I don't have such intuition about what's a good tensor and bad tensor for obtaining a balance.
That's only because we can compute. The border rank is in a range, we can compute it. That's what makes it, so we know its cost exactly.
Any other questions?
I agree.
Okay, let's thank her again.
Actually,